Hello, this is Dr. Muhammad, and this is another video under the analysis of statically indeterminate structures. Today I'm going to talk about the moment distribution method, and I am going to give a couple of examples regarding frames with Sidesway because I think it is important, and at the same time we need to emphasize on the main concept of solving frames with Sidesway using moment distribution method. So I'm going to explain this through a couple of examples. So let's go with the first example here. Let's see how it works. So as you can see here, we have the first example. It is like a frame with 20 feet high for member AB fixed at the bottom at point A, and it has BC, span BC, which is loaded with 2 kips per foot, and at point C it is roller. There is a concentrated load at point B with 25 kips, and for the span of this BC it is 15 feet. EI is constant for the whole frame. First of all, this frame, as you can see, it is frame with Sidesway permitted. Simply, as you can see here, at the horizontal line BC, there is nothing is going to stop points B and C to move laterally, especially that there is a concentrated load at point B, and there is a roller at point C. Even that member BC is inextensible, the axial deformation is negligible. However, B and C, they are going to move as a rigid body motion, and Sidesway is going to be permitted in this case. Whenever that we look to the moment distribution, we think about what are the points free to rotate, and based on this we are going to choose it to be our main point for making the balancing and carryover and distribution factors and so on. So as you can see here, we have 3 points A, B, and C. Our structure is having this point, which is point B, and it's considered to be free to rotate, the point that is free to rotate. Point A is not free to rotate because we have a fixed support here. Point C, it is free to rotate actually, but the point that we know the moment at point C, right? The moment here, it equals to 0. So this means that point C is excluded, point A is excluded. However, point B, it is the only point where that the theta or the rotation is free. We do not know it, and the moment is not known. So based on this, we are going to concentrate on this point, which is point B. Okay, now let's go and see what we are going to do. As you know, we have 2 parts for the solution of the Sidesway permitted frame cases. The first part is related to, this is part 1, which is related to the case where that Sidesway is prevented. In this case, we are going to prevent the frame from being swayed laterally. How we can do this? By adding a fictitious support at point C, for example, here, and then we are going to calculate the reaction that is going to be developed. So this is the first case, which is, or the first part, which is the analysis of the system based on the concept that the frame is Sidesway prevented. And the second part, which is going to be based primarily on Sidesway permitted. Sidesway permitted. In this case, we are going to remove all the external loading, and we're going to allow the frame to go laterally or to permit the side sway of the frame, and we are going to put the fixed end moments and so on, and then we're going to work using our moment distribution method as we have done before in the previous videos, and then we are going to end up with the relation for predicting the moment at the ends of the member, which is going to be m equals to m node, which is the original case of the side sway prevented, plus r, which is the reaction at the fictitious support that we put, over q, which is the value of the reaction in the case of the side sway permitted, the force that we're going to apply, and mq is the moment that is going to be developed at the ends of the members due to this q. Let's go from the very first beginning and start working with the same procedure that we have already set in the previous two videos. So for part 1, before going into part 1 and 2, we need to think about the point B, and we need to think about what are the distribution factors at point B. So the distribution factor, as we said before, it is factors that is going to be added at point B to distribute the moment between member B, C, and member B, A. So we need to have two distribution factors. From the example that we have the KAB, which is the relative stiffness for member AB, supposedly to equal to KBA, which is the relative stiffness also from B to A here, because the far end is fixed here and the far end is considered to be fixed here. So we are having the relative stiffness KAB and KBA, they are going to be the same, and this relative stiffness, as far as the far end is fixed in both cases, we're going to use I over L. L in our case it is 20 feet, so we have I over 20. Okay, so this is the case, and this is what we have obtained here. So we have KAB, which equals to KBA, and it equals to I over 20. So KBA equals to I over 20. We are going to put it here. This is the distribution factor. Remember, this is the distribution factor that we put in the first row for the moment distribution of the side sway prevented case, or part 1. On the other side, we need to know what is the other distribution factor, which is KBC, relative stiffness at the the distribution factor to the right of point B. Okay, so it is going to be KBC. Actually, we are going to find that looking here, BC, KBC. So if you going to predict KBC, it is going to be the far end is hinged, so it is going to be 3/4 times I over L. So we have I over 15, right? So this is KBC because the far end here is hinged. So based on this, we know now KBA, which is I over 20. We know KBC, relative stiffness, for the relative stiffness at point B with respect to the member BC, which is 3/4 I over 15. Then we can put the distribution factors easily here. So the distribution factor for BA is going to be equal to, the denominator should be the summation of the two. So the denominator should be the summation of the relative stiffnesses of all members framing into point B. So we have I over 20 plus 3/4 I over 15. This is in the denominator. In the numerator, we have BA. We're talking about BA. So BA, it is I over 20. So we have I over 20 here. So this means that we are, if you calculate this, you're going to find the distribution factor for BA. It is going to be 0.5, right? Without thinking too much, the distribution factor for BC, which is the other point or the other hand or the other side of point B, is going to equal 1 minus 0.5, because we have only two members framing into point B. This means that we are going to have two distribution factors. So if this one is 0.5, which is BA is 0.5, definitely distribution factor for BC, it is going to be 0.5 as well, right? Because the summation of the distribution factor at the same point should equal to 1, as we have explained before. Well, this is the first case, which is the distribution factor here at point B, 0.5 and 0.5. Okay, now the distribution factors at AB and CB, it is not important for us. We're not going to use them. Why? Because at point A, it is fixed. It is fixed means that it will have only carryovers, which is going to be obtained from the balancing of point B. And for point B, we know the moment. It is going to be 0 here. So we're going to make only one balancing cycle. Okay? So we do not need to distribute anything here. There is nothing to be distributed here. All the distribution supposedly is going to be to the moment that is going to distribute it is 0. So there is no need to put any distribution factors here, because at the end we are going to have 0 moment at this end, because it is hinged case. Okay, so now we understood what is the distribution factor, which is the first case or the first step in our analysis. The second step is the fixed end moments. If you look to the system, let us clean here everything. Fixed end moments here for member AB, we do not have any loading. So this means that there is no fixed end moments for member AB, which is FEMA or FEM fixed end moments AB or fixed end moments BA. They are going to be 0. So here we're going to put 0 and 0, right? For member BC, as you can see, we have external loading, which is 2K per foot. And there is concentrated load at point B. As you can see, this concentrated load will not produce any kind of fixed end moments in member BC. However, this distributed loading, because it is perpendicular to the span, it is going to develop fixed end moments. This is going to be calculated. Okay, so the fixed end moments with the end, we have B and C here, so fixed end moments here is going to be with this direction, and the value is going to be WL squared over 12. You can obtain it from the front cover of the textbook, as we have explained many times in the previous videos, and these values are going to be 37.5, as you can see here, and minus 37.5. They are the same in magnitude, but they are different in sign. This one is going to be positive because it is counterclockwise. However, this one is going to be negative because it is clockwise, as you can see here. So now this is the second step. We have the first step, which was the distribution factor. We already explained about it. And now the second step is the fixed end moments we put it. Remember that we are talking about our case, which is part 1 without sidesway, or sidesway prevented. Now, what we are going to do, what is the main reason for this? For two main reasons, actually. We are going to use the final moment here, which we call it M node, this is going to be used in our equation, and we are going to calculate R, which is going to be used in our final calculation. Remember our final calculation, our final member end moment equal to M node plus R over Q times MQ. Do you remember this? So from side sway prevented, which is part 1, we are going to get M node and R. That's what we are going to obtain. Okay? And then from the next step, we are going to obtain Q and MQ. So now, after obtaining the distribution factor and the fixed end moments, we are going to use the usual way for moment distribution. Okay? So we are going to use our moment distribution procedure, which is already we have explained in the previous 2 videos. Okay? Simply only for kind of reminder, we have here at point B, we have 37.5 unbalanced moment. We are going to distribute it with different sign, take care. Half and half, because we have distribution factor 0.5 and 0.5. This means that we have 18.8 here and 18.8 here with negative signs. And for point C, at point C, we have minus 37.5. It is going to be distributed to the same branch, which is CB. We can assume as if that the distribution factor here is 1, but again it will not add anything for us because they are going to cancel one another. They are balancing one another because we are going to have it 0 at the end. Okay, so do not bother yourself with the far end to be hinged because it is going to only make one carryover. That's it, and then stop everything. You are not going to continue with this point or with this branch. Well, we are going to draw a line here. This is the end of the first balancing cycle, and then we are going to look what is remaining. If you look to these values, they are balancing one another, so it is 0. The only thing remaining is what we are going to have here from the carryover from the branch, this branch which is coming from CB 18.8. We are going to balance it, as you can see, with the different signs. As you can see, minus minus because it is positive here. So we are going to distribute it and balancing here, and then this balancing is going to make carryover half here at the far end fixed, and before it also it was carryover far end fixed. That's it for us. We are going to stop it here because this point B in this cycle, it is balanced already, 0. So there is nothing else to balance, nothing. In this case, we are going to end here and sum up every column. As you have seen here, we found that ending up and summing up the moments, it gives us these values at the end. So what we call these values? M node. Yes. What is the meaning of M node? It is the moment at the member ends due to side sway prevented case. Okay, we are going to use it here in this final moment for the member ends. Okay. Now this is the M node, as we said. Now we want to obtain the second part, or the second important parameter or value for the equation, which is R. So what is R? Remember that we have put a fictitious roller support here, and this support supposedly to develop reaction. So we need to take into consideration this reaction. Okay, so we want to know what is the value of the reaction. We have developed a simple way in the previous video of how we can obtain this R. Simply from the M node, we are going to look to the columns, and we are going to put the M node at the top and bottom of the column. As you can see here, the bottom of the column, the value of the moment is 14.1, which is 14.1. This negative sign, it means that it is clockwise. As you can see, it is clockwise. At point B, the moment that should be applied at point B is 28.2. 28.2. And the negative sign here means that it is clockwise. Well, now we have the end moments of this column AB. We want to know how much shear that is going to be developed at the bottom and at the top of this column AB due to the induced M node at the end of this column. Then we're going to simply take the moment here at point A, and then we're going to find that we need to have a coupling moment that is coming from or produced from the shear at the top and bottom of the column. So this means that we need to have a value which is 2.11. Actually, this 2.11 coming from 28.2, which is this value, plus 14.1 goes this value of the moment. Both of them, they are divided by 20, which is the arm length here, in order to make a couple. And if you can see, the end moments at the bottom and the top, they are making clockwise moment. This means that our shear at the top and bottom of the column should make exactly a kind of counterclockwise moment, as you can see. Okay, so if you calculate this value, you're going to find it is 2.11, which is the shear at the top and the shear at the bottom. Okay, so this value 2.11, it is the shear of the bottom. This is an important for us because we are going to put it here in the system with everything in its position, but we are having R here. We want to calculate what is the value of R. We found that this 2.11, which is the shear at the bottom of column AB, it is heading to the right, and we have the original loading. It was 25K applied at point B. Both of them, they are going to the right. This means that R must equal to 27.11, and it should counterbalance them to obtain the equilibrium. Okay, so now R is 27.11. Okay, and this is the value that we were searching for. This is the value that we are searching for. Okay, okay, now let's go to the next part. Now we have obtained M node and R. Now let's go for Q and MQ. Okay, now this is Q and MQ is going to be obtained by part 2. What is part 2? It is sidesway permitted. Sidesway permitted. In this case, we're going to remove all the external loading, and we will allow, or we will apply a kind of lateral sway, which is delta prime here. So as if that we're pushing the structure laterally by a kind of delta prime. Okay, where is the external load? There is no external loading here. Okay, as we have explained in the previous video. Then if we are going to apply this delta prime, you are, as you can see, the elastic line of the column AB, this AB is going to be AB dash or AB prime. This means that there is straining actions that developed in member or the column AB. However, for BC, it is as if there is a rigid body motion happened for it, right? A rigid body motion happened to it. So there is no straining actions will be produced here. Okay, so in this case, we are going to say we want to know the moment distribution factors, which already we have like obtained in the previous step. Now we want to obtain the fixed end moments. What is the fixed end moments that is going to be developed here and here? Now the fixed end moments at AB and BA, it is going to be the same, because we have delta prime, which is movement of the top of the column by a fixed lateral displacement. The moment that is going to be developed, as we explained it before, 6EI delta prime over the length to the power 2. The length here is 20. Then we have This is the value. But here we want to know what is delta prime, how much that this delta prime here. Commonly we can assume it, but more conveniently we are assuming the output here. We assume the fixed end moment itself. It is better, okay? It is easier, that's it. So we're going to assume fixed end moments AB, which equals to fixed end moments BA, because both of them, they are the same. We're going to assume it 100 K foot, okay? It's an assumption. This means that the corresponding delta prime, it is something, some value. It's not important to know what is the value here, but we are knowing that we have assumed the fixed end moments to be 100. There is a corresponding delta prime here, okay? Okay, now let's go to the second part, which is the moment distribution. We're going to make the moment distribution here. So the first step in the moment distribution is the distribution factor. 0.5 and 0.5, the same as the previous part 1. Here, the fixed end moments, which is the second part, fixed end moment, we have assumed it AB and BA, they are the same, 100 and 100. Take care, they are having the same sign. Fixed end moments for member BC, there is nothing. No fixed end moments here. Why? Because we said that it will translate as a rigid body motion. So there is no straining actions that are going to be developed. Consequently, the fixed end moments are going to be zeros. Then we have a very simple moment distribution method or moment distribution table. We can distribute this 100 moment half and half here with different signs, carry over only once, and then we are going to obtain that this is the MQ case. This is the MQ. Now we put this MQ. All of these values, they are MQ. So they are helping us for the final equation. Right? Okay. Now this is what we call it MQ. Now we want to know what is the value of Q. How much force that we have applied laterally to make the delta prime or to make fixed end moments at AB and BE equal to 100. We want to know what is the value of it. So now we are going to obtain the value. How we can do it? We are going to take the moment from this table, which is 75, it is positive, and we are going to put it here. Positive means that counterclockwise, and the 50, which is positive also, it is counterclockwise, and this is for the column AB. What is the main reason for this? We want to obtain the shear at the bottom of the column. So from here, by taking the moment equilibrium at point A, simply we can obtain the shear at the top and bottom of the column, right? Then this value is going to be 50 plus 75 over the moment or this lever arm, which is 20. We're going to find the value here, 6.25, which is the shear at the top and the shear at the bottom, both of them with the same magnitude but different sign in order to make a couple. This couple, as you can see, it counterbalance the couple that is being developed by the moment at the top and the bottom. Okay, so we have this counterbalancing moment. Well, now we have obtained from this story, we have from this little story here, we want only 6.25, and we're going to put it here on the original frame without any kind of external loading. So we have 6.25 K applied or developed at point A, the bottom of the column AB. Then we need to balance it by, or at least this is the applied, or we can say the force that we have applied on the system in order to make delta prime, in order to make FEM or fixed end moments 100 at member AB. So this 6.25, if it is applied at point C, it will develop fixed end moments 100 and 100 at the top and bottom of column AB. Then we obtained now this 6.25 from the summation of x equal to 0 for the entire system. We can find that Q equal to 6.25 heading to the right, which is opposite to the shear at the bottom of column AB. Then 6.25, this is the piece of puzzle that is remaining for us, Q here. So now we obtained MQ and Q, and from the previous step, part 1, we have obtained M node and R. Then our actual member end moments are going to be easy to be obtained. So MAB, for example, it is minus 14.1. This is M node. If you want to be sure, let's go and check. This is here. This is M node. Minus 14.1. Okay. And here, sorry. And here we have, this is R, as we have mentioned before. And we have, this is Q, as we have already obtained. Then multiplied by MQ, which is 75 here. This gives us 311.2 Kep's foot. You can make the same for the remaining fixed or for the remaining actual member end moments. Okay, the same strategy. Okay, so now this is a case, the first example for us using the moment distribution method and using the two-part steps that we have explained before. Now let's go to another example, example number 2, and let's see how we can apply the two parts of our procedure in order to get the member end moments. So this is the frame, as we can see here. The span of the frame is 40 feet, and the height of the columns 30 feet. The distributed load is 20K at point C, and the loads applied is 20K, concentrated load 20K at point C, and the distributed load of 1.5K per foot along the span CD. The inertia is different. For the columns it is I, for the beams it is 2I. Okay, and Young's modulus, it is constant for the entire frame. Now let's go and apply the same two steps. So I'm going to be a little bit quick here because we have already understood the main idea. So part 1, no side sway, as we have done before. So here we are going to put our system as it is, and we are going to obtain the distribution factors. First of all, the 2 points which are free to rotate, they are C and D. So we are going to use only C and D to be as our pivot in our table. And point A and B, they are constant, they are fixed supports. So this means that they are going to receive only carryovers, and there is nothing would be emanating from them. Okay, so that's easy for us. And now we are going to balance and carry over 4 points C and D only. So the first case is the distribution factor. How we are going to obtain them. So distribution factor at point C, we have two distribution factors, CA and CD. So for CA, it is going to be I over 30, I over the length 30, and the denominator is going to be the relative stiffness that is framing into point C, which is I over 30 and 2I over 40. Okay, so 2I over 40, which means I over 20. This gives us 0.4 here. And for CD, which is this part here, CD, it is going to be, without thinking too much, it should be 0.4. So it should be 0.6 because it should equal 1 minus 0.4. Okay, it gives us 0.6 directly. So this is 0.6 here. If you are going to apply the same philosophy at point D, because of symmetry, you are going to find everything the same. So here it is going to be 0.6 and here it is going to be 0.4. So do not spend too much time in calculation of the distribution factor. It can be obtained easily just by investigation. Okay. The second is fixed end moments, which is very clear for you. We do not have any loading here, at point at members AC and BD, so there is no fixed end moments. Here 0, 0, and here 0, 0. However, for member CD we have this distributed load 1.5, so there would be some fixed end moments here. This one is going to be positive, this is going to be negative. From where you can obtain it? From the front cover of the textbook. It is going to be 200 and 200. This is negative, take care. Okay, what about this 20K? It will not make anything. It will not make any fixed end moments, okay? Because it is fixed end moments will be developed whenever there is on the members, whenever there is like perpendicular loading on it. But this one is not perpendicular on anything, okay? Okay, now we are going to make the same strategy. I'm not going to repeat it because I have repeated many times. You can go through the table, and at the end you are going to obtain M nodes, M node or the original moment here. Remember that in our case we want to get the main two parameters, which are M node, and then we need R, which is the value of the R, which is the reaction that we are going to put at the fictitious roller. Okay, so actually here we are going to put, if we're going to put fictitious roller at D, for example, okay, this means that, or we are going to put a kind of support at D, then there would be R should be developed. I'm going to talk about this point. But now these are the M node that we have. Okay, take care of the signs here. Already we have the M node. Okay, regarding R, if we are going to look, I'm going to clear this here to make it easy. Regarding R, actually if you look to the system, our system is, we are going to put like something here as like a roller and say that R is going to be here, right? But actually this is supposedly to have 20 here also, right? This is the actual loading condition. But if we remove, if we look to this system without the 20, without this 20, okay, you're going to find that it is symmetric in terms of geometry and in terms of loading. This means that there is no kind of lateral displacement will take place, and in the same time the shears that is going to be developed at the bottom of member AC and member BD, they are going to be with the same magnitude and having different signs, so they are going to cancel one another, and R would not take any value from the shears at the bottom. This means that R must equal to 20, which is the external loading applied on the system. So that's here, if we put it here. So R must equal to 20 directly. So this is kind of convenient way to obtain R. No need to make like the deep analysis for the column AC and column BD and see what is the shear at the bottom. You're going to find the shear at the bottom is going to be the same with different signs. Okay, look here, this is the moment, right, for member AC, top and bottom. They are exactly the same for the moment of column BD. But what you can notice here, that this is negative, this is positive. Consequently, they are having the same length. This means that the shear here is going to be the same as the shear here. So they are going to cancel one another. And the only remaining thing to make R, or to counterbalance the R, is going to be the external loading, which is 20. I have put it as a notice here. From the symmetry of the distributed loading, only distributed loading, take care, and geometry as well, the bottom shear of the at the columns will be the same with different sign. Then it will cancel one another. The only remaining is the 20K at point C, which is the external loading that we have. This means that our R is going to be 20. That's it. So now we have M node, and we know R equal to 20. These are the two things that we want from part 1. Now let's go to part 2. In part 2, we are going to allow side sway. As you can see here, side sway is allowed by putting some Q here. We put some force Q here. As we have done before, we are, instead of assuming delta prime, we are going to assume the fixed end moments that is going to be developed at column AC and column BD. We assumed them to be 100 k-foot. So we assumed the fixed end moments at A and C and B and D, they are the same exactly, because they are in the same direction. So we are assuming these fixed end moments to be 100. Then we're going to make a simple moment distribution. So we have the distribution factor as we have done before. We obtained it from the previous part. Here the moment, fixed end moments, 100, 100. Here it is 100, 100. In the middle, there is nothing. Okay, in the middle, there is nothing because there is no loading. And there is, if we go back here, rigid body motion for this member, rigid body motion. The columns only have the straining actions, but CD does not have anything. So in this case, we are having 0 and 0. Making the moment distribution as we have done many times before, you are going to end up with the last line here. It is MQ. This is what we are searching for. Okay, this is what we are searching for. We are searching for MQ here. Remember that our final moment is going to be M equal to M node plus R over Q times MQ. Already we have obtained M node from the previous step. R, we know it well, it is 20, as I have explained before. Now we want to know what is MQ. MQ is obtained by this table, and the remaining part as Q. How we can obtain Q? It is from the same strategy that we have obtained or we have explained before, looking to the shear, bottom shear of the column. So we are going to take the column and separate it here and put on the bottom and the top the moments that is going to be applied. The moment is 84. Let me clean everything here. So we have 84.6. We'll put it here. And it is counterclockwise because it is positive here. And 69.3. It is positive, means that it is counterclockwise, as you can see it here. Taking the moment at the bottom or taking the moment here, then you can obtain the shear at the bottom of column AC. This shear is 5.3. Then we're going to put this 5.3 at the bottom of the column AC, and similarly we are going to put it at another column. We will do the same for BD, the same moment, balancing of the moment here. We are going to do it for column BD, and we're going to obtain the same magnitude of the bottom shear. Then this means that 5.3 plus 5.13, it gives us Q, which is 10.26. This is the remaining piece of puzzle for us, Q. That's it. Then we're going to apply this equation in order to obtain the actual member end moments as we have done in the previous example. Okay, I hope that you have understood these two examples and they made you well acknowledged with the moment distribution method and how we can apply it in different cases. Thank you very much, and I think that I hope that to see you in the next video.